Here we have a statically indeterminate frame subjected to a concentrated load and a uniformly distributed load. We wish to analyze it using the force method. The frame has a degree of indeterminacy of 2, so we need to pick 2 of the reactions as redundant forces. Let's make the support reactions at C redundant. After removing the redundant forces, the frame is going to deform like this. We can refer to the horizontal displacement at C as delta x and call vertical displacement at C delta y. Then we can write the compatibility equations this way. Now we need to calculate these displacements. Here is how we calculate delta x. Let me explain what we have here. Here we have the support reactions of the statically determinate frame. Since we are going to write the moment equations for the frame members, we need to identify a bottom fiber for each member. This has to be done for the sake of consistency when using the beam sign convention. To write the moment equation for member AB, we are going to cut the member at some distance x from point A like this. Then we apply the moment equilibrium equation to get MAB. We do the same for member BC. Here, I decided to use C as the starting point, so x is going from right to left. This makes the free body diagram simpler to deal with. Summing the moments about the cut point, we get MBC equals -10 x squared. Okay, now we need to calculate M star. Since we want to determine delta x, the virtual unit load is placed in the x direction at C. Again, we need to write the moment equations for the frame members. For member AB, we get x minus 5. For member BC, we get 0. The member does not carry any bending moment. It just carries an axial load. To get delta x, we need to integrate m times m star. Here is delta x. Now let's calculate delta y. Since we have already calculated bending moment equations due to the real loads, we just need to write moment equations due to the virtual unit load. Here is m star for member AB, and here is m star for BC. When we integrate m times m star, we get delta y. We have 4 more displacements to calculate. First, let's determine delta xx. This is horizontal displacement at C due to a horizontal unit load applied at C. Since the unit load and the virtual unit load are applied at the same point and in the same direction, m and m star are going to be the same. Here is the moment equation for member AB, and here is the moment equation for BC. The integral of m star gives us 125 divided by 3 EI. Delta YY is calculated in the same manner. This is vertical displacement at C due to a vertical unit load placed at C. Next, we need to get delta XY. This is horizontal displacement at C due to a vertical unit load at C. In this case, M and M star are not the same since the real load and the virtual load have different directions. Here are M equations. Here are M star equations. Finally, we calculate delta Yx. Here, we want to determine vertical displacement at C due to a horizontal unit load at C. So what we referred to as M when calculating delta xy becomes M star here, and the M star we used for delta xy becomes M here. Not surprisingly, delta Yx equals delta xy. Now we can write our compatibility equations and solve them for the redundant forces. The remaining unknown reaction forces, there are 3 of them, can now be calculated easily using the equilibrium equations.